Well, folks, this is the last one, the last video. Thank you for staying on the journey with me. Just to finish things off here, I'm going to talk about a much more down-to-earth example. Something that's a little discouraging about the halting problem and such. Let me just say, no computer can solve the halting problem. This, I think, is very interesting, in my opinion, that there are basic limitations to what computers can do, and I'm not talking about the fact that just like the way that we build computers or something. No, it's not about that. It's about any kind of physically constructible computing machine has basic limitations. No computer can solve the halting problem and other things, right? The LU language is not computable by a Turing machine, but the halting problem is, I'll just say, or compute this language, LU, right? No Turing machine can have this as its language. When you tell your friends, tell your moms, tell your pops that there are limitations to what a computer can do, they will naturally say, "Oh yeah, well, what's an example of something that no computer can do?" And you say something like, "Well, no computer can decide whether some other computer is going to halt when you give it a certain input." That is a little unsatisfying because it sounds like you're just saying a bunch of nonsense about computers and other computers. I would really like to have an example which doesn't have to do with other computers, right? These are questions that you're trying to compute the answer of a question which is about other kinds of computations, which is a little weird. I want to talk about a much more down-to-earth example, a specific uncomputable problem that is a specific problem for which there's no algorithm to solve, that's not about other TMs, not about other Turing machines. So this problem, which I'm going to describe to you, seems like a more or less ordinary sort of math puzzle problem. I'll describe a situation, then ask you, like, can you figure out how to do blah, 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 blah. It turns out this problem, which I'm about to describe, cannot be solved by any Turing machine, even though it is not a problem about Turing machines, or it is not a question about the nature of computation or this weird stuff. It's a very specific, down-to-earth kinds of problem, and it's called the post-correspondence problem. PCP, all right? The post-correspondence problem. And I will write PCP. This was invented by a guy named Post. I know two things about Post. First is Post was a student of Alonzo Church, who I mentioned a time ago. He's the guy who invented a thing called the lambda calculus, which is sort of a parallel approach to the theory of computation, which is equivalent to Turing's approach, but completely different looking. It looks totally different. But anyway, Church was another of the great fathers of the theory of computation, although he gets less recognition from the mainstream today, just because he didn't invent computers, which is a considerably bigger deal to most people. Anyway, Post, that was the one. Post was a student of Church, and also Post was apparently Post was the first person to use the word string in computer science to refer to what we call strings. Post invented that term, I guess. I've always wondered why we call them strings. In my opinion, a string, the word string to me conveys something which is like wiggly and floppy, which a string in, like a computer string, is not wiggly at all. It's kind of long. I don't know. It's not a great word, in my opinion. But anyway, the post-correspondence problem. Let's talk about this. Actually, Post invented this little sort of math question, and his problem was invented in order to be an example of a ordinary looking question which actually cannot be solved by any Turing machine. Here it is. So it's sort of a puzzle. You could easily make like a phone app out of this where it's like a little game or something. Given blocks like this, I'm just going to draw a bunch of blocks. It's a little puzzle, right? And the blocks have strings on them, and they have string. There's always going to be one string on the top and one string on the bottom, and they can be empty strings if you want. This is a specific example of a post-correspondence problem. This one is called the starting tile. These are the other tiles. Anyway, here's another one. 1, 1, and on the bottom 0, 0, 0, 0, and 1, 0, 1, like this. All right. Let's say we are given some tiles like this. There could be any number. Here I have 4, and one of them is designated as the starting tile. And your job, the question is, can you find, or is there a sequence of these tiles, and you are allowed to repeat them? Repeats are allowed. Which starting with the starting tile, your job is to sort of line these up. Imagine that they were like dominoes or something. And you can use them more than once, individual ones more than once. Can you line them up such that after you line them up, you read the string across the top, and it is the same as if you read the string across the bottom? This is the post-correspondence problem. So, is there a sequence of these tiles with repeats allowed, starting with the start tile, such that the string read across the top equals the string when you read across the bottom? That's the question. I can imagine making a little phone app out of this, where you have these at the top, and then maybe I tap on some of them. I got to tap on this one first. That should go first, and then I got to choose some other ones in some order. You can choose as many as you like, right? This because I'm allowed to repeat them. I could choose this one, 10 times to start off with, and then maybe fill in the rest. You got to do it in such a way that when you're done, you line them all up, and the string when you read it across the top is equal to the string when you read it across the bottom. You can make this into a phone app. It turns out there is no algorithm to compute answers to this question. It is impossible to program a computer to answer this question for you. This is kind of shocking to me that some more or less ordinary looking puzzle, you can't make a computer to solve it. Other puzzles, certainly you can. You can write a computer program to solve Sudoku puzzles or whatever. That not this though, for some reason. Anyway, can we just look at this particular example? Look at these tiles. Maybe I'll erase my words here and see if you can solve the problem. Now, don't ask me about a general method by which this problem can be solved, because I'm here to tell you there is no algorithm to solve this problem. But you can try. You can still try to solve it, and sometimes you can if you in specific examples. Maybe this example is easy to do, right? Here it is. I wrote down my answer to this. You got to start with this one. So I'll start with this one. This is the starting tile. And now, let's see. There are some vague strategies you can try to use here. Like, when I read the string across the top, it's going to start with 1, 0, 1, 0, 1. That means the next thing that I put here needs to have a 1 here. That's because down here, it starts with 1, 0. And if the string across the bottom is going to equal the string on the across the top, then it's going to need to have a 1 next, right? And if you look at my options here, there's only one that does have a 1 here. So apparently I must choose that for my next choice. All right, can we continue to reason this way? Now across the bottom it says 1, 0, 1, 0, 1. The top says 1, 0, 1, 0, 1, 0, which means the next thing that goes down here needs to be a 0. Now actually I have two choices, this one or this one. But in this particular example, you get kind of lucky. You can rule this one out. Actually, you should never use this tile because it puts 4 consecutive zeros in the bottom string. but there's never an opportunity to get 4 consecutive zeros on the top string unless you did that one 4 times, which seems unlikely to do this one 4 times. Anyway, don't do that one. Let's do this one instead. And I think actually now this is a solution. When you read the top string across, it says 1 0 1 0 1 0 1, right? And when I read the bottom string across, it says 1 0 1 0 1 0 1, and they are equal. Hey, I did it. All right. I just did something no computer can possibly do. Actually, it's not true. You could make a computer that solves this one example. What I'm telling you is there is no general procedure which can solve any example of this PCP type problem. I want to try to explain how it is that Post was able to show that no algorithm can solve his little puzzle here. So Post showed that the PCP was unsolvable by any algorithm. Can I just say, this is another word that people use for this, uncomputable. That means you cannot compute the answer to the problem by any algorithm, by any Turing machine. He showed that PCP was uncomputable by, this is a very common strategy that people use to show various things are not computable. He called it, or people call it, reduction to LU. That is to say, Post showed that any solution, I'll say i.e. any PCP solver, if you could imagine some kind of Turing machine or procedure which can always solve the PCP, any PCP solver can be converted into a Turing machine for LU. And that is impossible because we know that such a Turing machine cannot exist. This is the way that most undecidable problems nowadays, people are still in this business trying to find problems which are uncomputable. Most of the time, to prove something is uncomputable, you show that somehow that question is equivalent to solving the halting problem or to solving this LU language, which we already know is uncomputable. Usually you don't prove directly that the PCP is uncomputable. You show PCP is somehow equivalent to Turing machines for the halting problem or Turing machines for LU. Anyway, I want to try to describe to you how is it that a PCP solver could actually be converted into a sort of Turing machine solver, which would allow you to compute this language LU. There is a procedure. I'm gonna start again at the top here. So let's look at this Turing machine. I'm just going to do a specific example here. Of course, Post, did this in complete generality. I'm going to leave out a lot of the details just because it gets pretty complicated, and really, all I want to get across is the basic idea of this whole thing. Here is a Turing machine, AAR here, AAR here. This state 2 has a loop edge, BBR. I don't actually care about really what this Turing machine does. BBL here, and it goes to an accepting state. This is a little weird because I'm actually going to give a name to this accepting state, and I'm going to have edges on the accepting state. This typically you wouldn't do in a Turing machine, but I'm going to say why in a moment. So this Turing machine, and I'm going to assume that our Turing machine, I'm going to say it clears the tape. Clears the tape when it accepts. Turing machines, as we've talked about them, as soon as they enter an accepting state, they just stop. But you can always change the Turing machine so that it clears the tape. That's what these transitions do. Once you arrive in the accepting state, now it goes back across the entire tape, moving to the left. If you look at the rest of this machine, it always moves to the right until it accepts. And then it's going to go back to the left and just blank out everything on the tape. And so what you will end up with is a completely blank tape. All right, this is a Turing machine that clears the tape. Any Turing machine you can imagine is very simple to modify so that it clears the tape. You just change the final accepting state into one which runs across the whole tape, clearing everything. All right, So we're just going to assume that our Turing machine clears the tape. And I'm here to tell you, if you had some kind of PCP solver, we can convert it into a algorithm to decide if some X is accepted by our Turing machine here. All right, I'm going to try to describe to you how you would do this. It turns out Post figured out a procedure whereby you could translate this Turing machine into a bunch of tiles. Let's see exactly how we do it. Unfortunately, I got to erase this. You will need to be looking at this diagram constantly in what I say next, so make sure you got that. So our basic goal here is to convert the Turing machine to a bunch of PCP tiles, and every transition will correspond to a specific tile in a specific weird format. And we're going to have special tiles to indicate where the starting state is, where the final state is, etc. So let's imagine, say we want to decide whether or not our machine M accepts, let's just do a specific example, AB. All right, let's say we want to decide specifically whether or not our Turing machine accepts AB. Now, in general, there should be no algorithm to decide whether or not some machine accepts something else. But I'm here to tell you, if you somehow had a PCP algorithm, you could convert that into an algorithm that will answer this question. Say we want to decide whether or not M accepts the string AB. Now, on the Turing machine, if you were doing this particular example as a Turing machine derivation, you would just do this kind of a thing, right? You would write 1AB. This is the initial state of the machine. We begin with AB on the tape. We're in state 1 looking at the A. And then can I just write down what would the actual steps be here? In state 1, when you read A, you move to the right, go to state 2. So it will now say A to B. In state 2, when you read B, you go to the right and stay in state 2. So this is going to say A, B, 2. Usually I would write another blank, but you'll see in order for this little conversion to the PCP to work, I'm not going to write any blanks here. This is actually a slightly important technicality, but I hope you will let me get away with that. Okay, and now when in state 2 we read a blank, we move back to the left and go into state 3. So next it says A3B. And then in state 3, it's just going to clear everything, blank everything out. So the next state will blank this B, move to the left, so it'll say 3A. Then it'll blank this A and move to the left, and I'll just be left sort of with a 3 here, right? Which eventually will go to nothing, except, can I just say, accept, right? So the question of whether a string is accepted or not is equivalent to saying, can I start like this and get down to nothing when we clear the tape, all right? That's why we're doing this clear the tape thing. It's just to conveniently make it so that a successful acceptance ends up running the tape down to nothing, all right? Here is how we translate this into tiles. So PCP tiles. First of all, we have just a bunch of basic tiles which represent the letters in the language. So there's A like this, B like this, and then there's also a special one like this. The idea is our tiles are somehow going to represent little chunks of this complete derivation, and then by assembling the tiles together, you can patch together a full derivation. That's the basic idea, so that if you, by some magic, were able to arrange the tiles properly, that same magic would allow you to make derivations on the Turing machine. They are equivalent procedures. Anyway, let's say these are the special tiles for the letters. And now I have some tiles for the, I will say, for the moving to the right. What the tiles are going to represent are sort of little before and after snapshots of every legal move. For example, the first move that we did, was a 1. We were in state 1 and looking at A, and this little 1A turned into a A2, and that's what I'm going to put on this tile. So at the top it's going to say 1A, and at the bottom it's going to say A2. So this tile represents the fact that if we have a 1A, we can move it and change it into a A2. All right. There are other moves to the right. You'll see the moves to the left actually are a little more complicated to write, but there are other moves to the right. On the diagram, you have to make a tile like this for every possible move to the right. There's also, from state 1, there's a looped edge with a B on it. And so that one is going to look like 1B, B1. This means if the head is in state 1 pointing at a B, it can read that B, move to the right, and stay in state 1. That little bit of the derivation will now look like B1. Okay, other rightward moves. There's one more. It says BBR on state 2. So this one will look like 2B, B2. All right. Those are all the, no, and there's one more that is moving from state 2 to state 1 with A. So this will say 2A, A1, right? If you're in state 2 reading at A, the head will move to the right and switch into state 1, and the A will stay like it was. Okay, these 4 tiles indicate the right-hand moves. There are some tiles which indicate the left-hand moves. These ones, unfortunately, have to be a little bit more complicated, and I got to erase all of this stuff, unfortunately. I hope you're writing everything down. If not, you're going to be pretty confused in a moment when I say, hey, look at that thing from before. Okay, now we also have tiles which represent the left-handed moves. These ones have to be a little bit more complicated. For example, let's look at the looped edges on state 3. Those are left-handed moves, which are replacing A with a blank or B with a blank. The way we have to write those is going to be something like this: A3A. So this says if you are in state 3 reading an A, and there was an A to the left, then the result of that should be the 3 moves over to the left. This A gets blanked. It should now look like 3A. And what if there was a B on the left side? Then it should look like B3A, 3B. And what if it was blank on the left side? Then it should look like 3A, just 3, right? This 3 will move to it will blank this A and then move to the left. There will be nothing left. It will be blanks everywhere. So that'll just be a 3. Okay, so these 3 tiles refer to that one looped edge with an A on it on state 3. We need similar things for the looped edge on state 3 with a B. So this would say A3B, 3A. That means if we're in state 3 and we read a B and there was an A to the left, we should move the 3 to the left. It'll now be 3A, and this B will be blanked. We also have B3B, 3B. And what if there was a blank to the left? It'll say blank, 3B, just 3. All right? Like I said before, I'm not writing any blanks. I think my marker is finally extinguished. There's one more leftward moving move. This is the arrow from state 2 to state 3 with blanks. So this is when you're in state 2 and you have blank on the right, but if there's an A on the left, this state 2 will turn into a state 3 and then move to the left, so this will become 3A. Similarly, if you had a B to the left of the state 2, this will become 3B. And if it was really blank to the left of state 2, this would just become a 3, right? If it was already blank over there, it would move over and you just get a 3 here. Okay, these are all the left-handed moves. I changed colors just because I ran out of ink there. There's no meaning to the different color. All right, there are 2 more tiles that I need. Actually, this is the full set, but there's 2 more just for the sake of putting the full set on the screen at once. Can I squeeze them in over here? 2 more tiles that we need. One is to indicate the starting state in the Turing machine. So this one indicates the start state. And this one is weird, but I'm here to tell you, here's what it looks like. And it is the starting tile. Remember, the PCP has a starting tile. It has the empty string on the top. And on the bottom, it has 1AB, like that. So what this means is we start in state 1, and we begin with the tape saying AB, right? This is how our Turing machine computation is supposed to look. Remember, we're trying to encode the Turing machine computation for the string AB into a bunch of tiles. So this is where that string goes and also tells you what state to start in. We start in state 1, and the tape begins saying AB. And then we have a tile to designate the accepting state. Now, ordinarily you might have several tiles of this format, but in our example there's only one accepting state, and it just says epsilon on the bottom. This is weird, like that. All right, I want to describe how it is that solving this PCP is equivalent to making a derivation on the Turing machine. So, if you can solve with these tiles, it will automatically be equivalent to showing that the Turing machine accepts. Let's try. So I hope you have written these all down. You're going to have to look at these while I'm trying to solve this PCP, but I got to erase them. Solving this PCP is equivalent, or say that no solution exists, is equivalent to writing a derivation on the Turing machine. Or, part of solving the PCP is either show me a solution or somehow decide that there is no possible solution. So, with those tiles that I had just indicated, solving that PCP problem is equivalent to either writing a derivation on the Turing machine for a particular string or explaining why there is no possible derivation for that particular string. So here's how it goes. In our example, we need to start with that starting tile, which has epsilon on top and then 1AB arrow on the bottom, right? And now, can we make a PCP solution here? That is, we have to write a bunch of steps here, which reads the same across the top as it does across the bottom. We can try and do some sort of simple reasoning along the lines of the other example of PCP that I showed. The fact that I begin with 1AB on the bottom and the empty string on the top means this here, whatever I write here, must begin with a 1, certainly, because this string, when you read across the top, is going to have to be equal to the string when you read across the bottom. In fact, if you look on your list of available tiles there, which ones begin with a 1? Actually, there's only 2 tiles on the list. I'm looking at my list right now. There's only 2 tiles on the list which begin with a 1. There's only one which begins with a 1A, and that is the one of those right-handed move ones. You must use, in this step, 1A, A2. All right? You must. I hope you are also able to look at the derivation of the string. Actually, maybe I'll write it up here. Check out the Turing machine derivation. Would you believe it? If I read this string across, it looks to me like I am actually building this exact string. This giant thing here is actually going to be the string that we get when we read across the bottom. And it will also be the string that we get when we read across the top. That's the whole point of the post-correspondence principle. But what you're going to see here, well, let's see, what should I have next? If you believe what I just said, the next thing that I should see along the bottom, I have 1AB, arrow, A2. The next thing I should see is a B. What do I want to see next on the top? Actually, it's also a B. So at this point, we're going to put this BB here. And then the next thing I want to see in both will be the arrow, right? Up top, it should say 1AB arrow. Across the bottom, I want to copy this. The next thing I see should be an arrow also. All right? What I'm looking at here is basically across the bottom, I'm going to be writing this entire derivation. And across the top, I will get the same derivation, but it's kind of one step behind, right? Here I have A2B, which is this string here. And at the same time on top, I have 1AB, which is the previous string. That's always how this is going to work, actually. The bottom, you will read this derivation. Across the top will be the same thing, but it'll be offset, like one step in the past. All right? Anyway, what should be next? A2B arrow. Okay, next I want to see AB2, and up top I want to see A2B. So I'm going to put the A block by itself, and then this is going to be the B2. and the 2b, right? There is a 2b, b2 block, isn't there? Yes, there is. Okay. So now I'm on the bottom, I'm here, and on the top, I'm here, one step behind. Next, for both, I want to see the arrow, so I'll put the arrow. Come on, buddy. Running out on the last video. Okay, I had AB2, A2B. Next, I should see on the bottom A3B, and on the top AB2. How can we make that happen? A3B, AB2. I think I need another A by itself, followed by, can I do 3B and B2? I think I can. Is that one of the tiles? You know it is. That is one of the tiles, all right? It's like magic. The post's basic idea was translate every little bit of this into tiles. And then if you can place the tiles properly, it means that you can write this derivation properly. Okay, next would be another arrow. That's what I need. And then next, so across the bottom, I want to see, after A3B comes 3A. So I think actually, is there such a thing with just a 3A on the bottom? There is. And on the top it has, actually there's two with a 3A on the bottom. There's one which on the top says A3A and one which says A3B. Actually, I want the top next to say A3B, so luckily for me, there is a tile which says exactly that. All right, now I do arrows again. Next step, after 3A, I just want to see 3. Is there a tile that can give me just a 3 at the bottom? There is, and at the top, it either is going to say, I see 2 actually, it's either 2 or 3B or 3A. And if you look at where the top computation is, it should say 3A on the top. All right. Then another arrow. We're almost done here. Actually, now I want to see, to copy this string exactly, this is the end. I want to see nothing down here, whereas up here I still need to have a 3. Is that possible, to put a 3 on the top and nothing? There is. If you look at that accepting state tile, there is a tile which says 3 followed by the arrow and then an epsilon. And this right here, this is a PCP solution. All right. And do you believe me now that deciding whether or not you can make PCP tiles in this example is the same as deciding whether or not a string is accepted? So the moral of the story is solving PCP is equivalent to deciding if some Turing machine accepts some string x. And therefore, solving PCP cannot be done by any algorithm, because this right here is that language LU, which we know already to be algorithmically uncomputable, right? LU is not recursive, so you cannot compute it by any algorithm. And so, that means automatically PCP is not computable, not solvable by any algorithm. There you go. That, I think, is a fitting conclusion to the course. I think this is to me, very interesting that there even is such a thing. A little sort of puzzle. No computer can solve the PCP. Weird but true. All right, I guess that'll do it. Thank you for your attention. It's a shame it had to end this way, but what are you going to do? Stay safe. Stay woke.